All right, greetings, students. Today I wanted to do a very quick tutorial on Lesson 7's discussion board question. I've had a couple of people come on up, and I've seen a couple of posts so far, and there seems to be a little bit of confusion with this. So I want to have a little demo for what you do, and to provide you with a bit of a tool that you can use. So, for those of you who are not familiar with, this is my website for the class, and all of my classes, in fact. Right now, I only have one at the moment, but as more adds, I will add. And I want to draw your attention specifically to my virtual science lab here, specifically the vector addition. So, I'm going to click on vector addition, and we're going to take a look at this and take a look at what we can use this vector addition software for. All right, now let me scroll this into the screen so you can see it nice and big. Okay, so this is an online simulator to simulate the addition of vectors. Now, when we're dealing with forces, which is the topic of the unit for this week, Newton's laws and forces, we need to understand a few things. First off, forces are represented as vectors. Not only do they have a numeric value in their magnitude or quantity or amount of force, but they always also have to have a direction as well. Forces and acceleration are similar in this way in that they have to both point in a direction and have a value. Same with velocity as well. Speed being our exception in that speed has a value but does not necessarily need a direction for us to discuss it. Now, as part of the problem you're working on, you are supposed to devise an experiment in which we test to see if we can design a three-way tug of war and if it can be balanced in such a way that it is fair to all of the teams involved and allows for three teams to compete at once in a tug of war composition where we have an odd number of teams. The thinking behind this is that if there's an odd number of teams, there's always a team that's basically getting to rest and therefore has an unfair advantage to teams that aren't resting. And so we want to eliminate that. So what they've asked is, can we design a three-way tug of war? Now, there's a couple of problems with this so far that I've seen in the answers. And the first is in a lot of it having to do with the design. A lot of people are missing this bigger idea of how do we design it and really this vector component of this. So let's take a look at what we're asking for here. So they want you to give a description of what the materials you would be using and how you would set the materials up with specific angles. So the angles at which the strings attached to the ring in the center of this experiment would have to be arranged to produce an even pull in all directions. All right. So let's take a look at what that would look like at vectors. So for this experiment, I'm going to use three different vectors here. And right now I'm setting them to be equal vectors. To represent the three strings and the three tension forces. Now, my goal here is to keep them to be the same 10 value, but the angle is going to change, and I'm going to have them all radiating out of a central point. Now, when I have three vectors together, and I want to add them together, as you can see here, these three, if added together, would produce this bigger force. So if I had three strings pulling on an object in this direction, I could sum them up and say this is the total force pulling it. So in this case would be 10 newtons, 10 newtons, 10 newtons, 30 newtons. And it's all in the same direction. Now, I'm going to include this as well. Let's take a look at some of the configurations. Now, say I want to add these forces together. Now notice, I'm turning this, and what I can see here are the components. So this is the X force and the Y force that add together to make the resultant 9.9. Let me get up it to 10. All right. Now I'm just going to move this here. Now you can see I'm going to take this force and I'm going to move it in opposing angle. Let's do... Alright, make sure it's still the same amount. And we'll move it here. Let's see, I'm going to move this to 1... Oops, too far. 10. Okay. So I've got a little bit of hard to make. Okay, now, if I had a ring attached here, even though I have two forces pulling here, their vectors are canceling out because if you look, there's only one resultant pointing this way, saying that the force would go this way. Okay? But what I want is a resultant of 0. And I want to move my angles. So here. Now notice, here I have an equal amount of force, but as soon as I get off of that balance perfectly lined up, my resultant starts to dip. This here is the actual direction that if I were to let this go, the system would move, the whole system would move. So what we're asking you to do, and I want you to play around with this, is play around with these vectors. Turn on, you can even turn on a grid too if it makes it a little easier to organize. But use style to 1, make sure that you're showing the sum, the total vector, and I want you to arrange these vectors until the green arrow completely disappears. So let me do an example. I'm just going to use 2 vectors. So I'm putting a vector here, and I'm putting a vector here. Okay. And I'm not going to... Alright, so this is my first. Now, I want this to disappear to 0. So I'm going to move this. So I've gotten that part to disappear, so I don't want to go. So now I'm trying to keep it to go here, here. Alright, so now I have it to 0. What that tells me is that if there were 2 people pulling on the string, they wouldn't move. They're perfectly balanced in their forces, which means they would have no acceleration. So unless they were already moving, there would be no change in their motion. This would be a perfect deadlock tug of war. Let's say I move this way. If they were to slightly move to the side, we'd see that the whole system moves this way. So to compensate, I would have to move this to there. And you can see their resultant are equal, but their directions are opposite. Therefore, we have a balanced or no force. Now, what I'm going to have you do is I want you to go to and use this simulator to figure out what 3 angles, so we're now going to have 3 vectors, at what angles do the 3 vectors have to be if they were equal forces, so that means they have to be equal lengths, and they produce 0 resultant force. So they have the green resultant force disappears. I'm going to move this over here. Okay, so I'm going to play around with this until I get almost perfectly. Oh, almost. Oops. There we go. So this would be an example. So now these are not equally pulling on the forces, so this would not be the best setup. In fact, these 2 have to pull less than this, so if this were their 3rd team, they would be having an unfair disadvantage. What we want is to get it so that the pull on the 3 is equal amount, and at what angles would they have to be arranged to produce an equal amount of pull so that there'd be 0 force. Now, this is just how the concept of this works. You do need to pay attention and be clear that we're also trying to figure out how could we design this experiment with actual real-world tools. So while I'm giving you this example of how to test this out virtually, this is not the final version that we're looking for in your description. So watch the video, go to the site, check out this simulator, and then come back and try your discussion then. All right.